Thank you very much for the opportunity to give this talk today. And so here are my disclosures. Nothing's really relevant for this talk. So we hear about AI all the time. We involve AI in some of our research. And I stopped to think, what does artificial intelligence actually mean? What's it getting at? How's it defined? And this is what I came up with to create smart machines to mimic human behavior. Immediately, my mind took me to this. Anybody that grew up in the 80s, I think, can relate, the T800, smart machine, AI enabled. But this was a talk about AI in medicine. So I asked Meta AI, what would it look like if the T800 was practicing medicine? And this is what came up. I thought, that's pretty close. Now I'm starting to understand this. We're getting a little bit closer here. But one of the features is to be human biomimetic. And of course, there's all the emotional intelligence. So I asked Meta AI, what it would look like if the Terminator was also experiencing infertility. Didn't look very happy, I could relate. And what about if they're experiencing erectile dysfunction? Now, clearly those are not FDA-approved blue pills, but maybe well suited for the Terminator. But fortunately, with AI and medicine and all the different applications, there's a lot of hope and forward movement in technologies, so help is on the way. Now, what does artificial intelligence mean in terms of, from a conceptual standpoint, how does it work? You have data that goes in, you have a desired output of what you want to get, then you use that to train something that's called a model eventually, and then that model can then work on new data and create that output. So it's about training something, then in a validation data set or a data set that you want to get something out of, you can put that new data into and you'll get the output. Now, how is this compared to regular or advanced statistical analysis? Well, there's a lot of parallels, but there's a little bit of differences as well. You put the data in, you have your statistical analysis, the program, and you ask a computer to crunch those numbers and you get the output. So here it's directly your in gets computed to your out, where in AI there's a training phase and then that model can then handle new situations. So it's a very simplistic non-computer scientist approach. That's how we can understand it. Now, this was just a quick little example. The whole idea is that AI and machine learning can handle really complex data. So this is a little example with a neural network of handling these patterns that regular linear statistics wouldn't be able to handle. But if you have several hidden layers to contribute to that, eventually it can solve some of these extremely complex problems that with a regular statistical analysis and tools, we wouldn't be able to solve. So we have the overall field of AI, artificial intelligence. Within that, we sometimes hear about things like machine learning. Machine learning is a subset of AI that is meant to handle complex problems through learning independent of some of the human input. Deep learning is that on steroids. As you could imagine, there's many more layers, and it's meant to handle much more complex levels of data. Then you have natural language processing. So this is understanding, interpreting, and generating human speech. And within that, you have these large language models like generative AI and some of the things like ChatGPT that we hear of, which is a combination of these two. So that's kind of how all these different terms work in together. Now, when we look at the applications, there's a lot of different use cases within medicine. So some of the current applications that lots of people are using is looking for trends within large data sets. This could be on a public health basis, this could be clinical data. Then there's image analysis, computer vision, and being able to try to diagnose or characterize or create digital biomarkers to better understand human disease, and we'll have some examples with reproduction shortly. It can also be used to help improve clinical trial performance, retrieving medical information, and then operational or logistic help in organization. Some of the future directions might be real-time integration of AI for enrolling into clinical care and providing assistance or help to healthcare providers, or even assessing healthcare providers or creating really advanced simulation centers. So when we look at these categories, what are some of the use cases that have been used in reproduction so far? There's been a lot based out of computer vision based AI. So this could be sperm assessment. That could be anything from quantifying a semen analysis type of parameters that we're used to. This could be assessing DNA fragmentation measures based on bright field images, sperm selection, embryo selection, egg evaluation. We can use it for complex data, so multi-omics analysis of cellular function, epigenetics, transcriptomics, or drug discovery pipelines. And then, of course, some of the things that are more accessible to us on a day-to-day basis, these language-based models. So this was one example of a paper published in 2019 from the Toronto group that was looking at SCSA staining of sperm to train a neural network to try to predict which sperm, just based on bright field microscopy, would have DNA fragmentation. So the top A and B, they trained it, they stained it with the acridine orange. They took those images and immediately took bright field microscopy images, trained the neural network, and then that trained model could then predict based on a new set of data. And so when they looked at 6 different donors, this is what they found. There's a correlation of about 0.43, and the x-axis is the actual measured DFI, and the y-axis is the predicted DFI based on the machine learning algorithm. And as you can see, it's not perfect, but there's certainly some associations here. And this is just looking at bright field images as you look through a microscope with no staining in the machine learning data input. And this is what the computer saw. So the left side is what sperm heads look like with the lowest DFI, and the right side was the highest DFI. So this pixel by pixel basis is what the algorithm is determining and seeing to differentiate high versus low. Now, another use case is post-tissue retrieval optimization for microtessy samples. This was a paper that we published a couple of years ago. And one of the big problems is that we harvest tens of millions of cells during a microtessy, and it's the literal definition of finding a needle in a haystack. And andrologists are going to be looking for hours trying to find 10 to 20 sperm in amongst all these other testicular cells. So it's a volume of information problem. So basically, we created a ground truth. We stained the sperm, trained the algorithm. As you can see here, you see the bright field image. The fluorescent image is the black squares. Ground truth is defining what that sperm is, train the network, and then it predicts what a sperm is, and then after it predicts it, you set a threshold, and it detects a sperm there. So this worked fairly well. It had 83% of the time, the sperm it said it detected were actually sperm. And then the recall, so what proportion of all sperm were identified correctly, was about 74%. When we mixed that in, that was mixed in with the testicular cells, and then when we diluted the sperm so that it was rare sperm amongst the testicular cells, it actually performed a little bit better. So that's just another use case example. In terms of using complex multiple sources of data, like drug discovery pipelines, this is how something like this could work for advancing in vitro spermatogenesis or something to that effect. You could have gene expression, small molecule databases, drug databases, nutraceuticals, and perturbation databases. So impact of a drug on a gene expression change, you put into the neural network, and then it can give you predictive molecules of what to test. So it can handle huge complex data sets. Finally, just one quick example on the female side of reproduction as well. This has been artificial intelligence and neural networks have been used extensively for predicting embryo quality and egg quality, and this is just one example showing that artificial intelligence with the pink bars far outperformed 10 embryologists in predicting embryos for biopsy or cryopreservation. So final point is just around ethical considerations. The field is advancing really quickly, and a lot of the ethical guidelines have to catch up. So generating some of these models, we have to be mindful of what data we're putting in. Could be biased from an ethical or from a patient perspective, socioeconomic status, demographics, racial inequities, et cetera. And there's a huge amount of data that's required to train these models. So in terms of ownership of sensitive data, some of the regulations kind of need to catch up and help out with that. So in summary, there's a huge amount of use cases in reproduction, a lot of opportunity. I think that's going to change the field in the next 5, 10, 20 years. And hopefully the ethical regulations can keep up with it as well. Thanks so much.